Maxima and minima problems, also known as optimisation problems. Basically, we're talking these word problems, which we're going to turn into an equation, which we then can use our maths to solve. A lot of things we're trying to find the best solution, maximum profit, minimum waste, things like that. So we want to optimise the solution, get the best result we possibly can. So the problem we want to reduce down to a set of equations. Now, the ones that we end up looking at, usually there's going to be two. In the real world, it could be lots of different equations because we're not limited to 2 dimensions in maths. We can go to n dimensions and look for the best solution. But pretty much we're going to be reduced down to 2. And so one of those should be what it is we're trying to optimise. What are we trying to find the maximum of? What are we trying to find the minimum of? And then the other one, or ones if we've got more than 2 equations, will be information that's been given to us. Maybe it's the amount of material we've got to use or something like that. So what we then want to do is get the equation that we're trying to optimise and reduce it down, in our case, to 2 dimensions. Because then we can create a graph and we can use our calculus to work out, well, when is it a maximum or a minimum, whatever we're trying to find. So here's a typical problem. I'm sure you've experienced it yourself. You've got a rope 36 metres long and you want to cut it into 2 pieces, but in such a way that the first piece you're going to make a square and in the second piece you're going to make a rectangle. It's something we do all the time. We want to find how big will that square be if the sum of the areas is going to be a maximum. Maybe we're creating 2 ant farms, and so they've got to be contained within the ropes, and we want them to have the maximum area they can roam. All right, well, I like to draw pictures to get a feel of what I'm doing. So I've got these 2 shapes, one's a square, one's a rectangle. Let's give it some dimensions, some pronumerals. Seems logical to call the length of the side S, so I'll make that S. And the rectangle, well, S, and the other one I'll call R for rectangle. All right, well, I'm trying to maximise the area. So let's come up with an equation for area. It'll be S squared plus R times S. Now at this stage I've got 3 variables, so I'm dealing with 3 dimensions there. I want to get this down to 2 dimensions. So I have another piece of information. The rope was 36 metres long. So I know that 6S plus 2R must be 36. Basically the perimeter of the 2 shapes is the length of the rope. I can now rewrite that second one to either make R or S the subject, it doesn't really matter which, and substitute it into the other one. And that will reduce the other one down to 2 pronumerals or a 2-dimensional problem. It makes more sense to make R the subject. So let's do that. So R is 18 minus 3S. Substitute it into the other one. And, well, let's make it look neater. There we go. We've got a quadratic, basically. Now, of course, at this stage, I don't actually need to use calculus if I recognise that's a parabola. Because if it's a parabola, then I know the maximum is going to be at the vertex. I could use my quadratic theory if I wanted to. But for the sake of the example, let's do it with calculus. So there's my formula. Differentiate it once, that'll find the stationary points. Differentiate it twice, that will classify my stationary points. So I'm trying to find those stationary points, the point that will give me the optimal solution. That's going to happen when the derivative is equal to 0. So S is 9 on 2. The second derivative is -4. In fact, it's -4 everywhere. Makes sense. If we're talking about a parabola, its concavity is not going to change. It's just concave down. In this case, -4 is the measure of that concavity. So that's all I need to do for this problem, because they never actually asked what is the area or anything like that. They simply said, find the side length of the square when the area is a maximum. Well, I've done that. I don't need to do anything more. So the side length would be 4.5 metres. Then the area is a maximum. That brings up something interesting. If the length of the square is 4.5 metres, what's the length of the rectangle? Obviously one side's 4.5 metres. What would the other side of the rectangle be? Yeah, it also turns out to be 4.5 metres. See, when we're optimising, the perfect solution very often is the optimal solution. So the rectangle's optimal solution is very often a square. Things like that. Okay, let's do this one. We've got a bucket. We're going to make a bucket. And we want it to hold the most liquid it possibly can. Makes sense. Well, the material we've got to work from conveniently as a multiple of pi, 12 pi units squared. We want to find how big is our bucket, basically. The height, the radius, the volume of this bucket we're going to create. Now this is a very simplified question because it assumes there is no wastage. So we're going to use every piece of material. In the real world, that doesn't happen. You're going to have wastage. That would be an additional equation to the problem. And so in the real world, we'd probably have a three-dimensional problem. But that's okay. You can still optimize a three-dimensional one. Instead of looking at just a shape like that, you've got some sort of surface. And you say, well, what's going to be the optimal solution for the surface in 3 dimensions? Still the same idea. But we're just going to do this simple one. Okay, there's my bucket. We want to find surface area of a bucket. Now, be careful here, because we do know the surface area of a cylinder. But that's not the formula I'm going to use exactly. The volume is pi r squared h. Okay, that's the same. That hasn't changed. Surface area, pi r squared plus 2 pi r h, which of course is not the surface area of a cylinder. But I haven't got a cylinder, I've got a bucket. I don't want to put a lid on this bucket, or there's no liquid going to get into it. So it's only 1 pi r squared plus 2 pi r h. Okay, I need to get rid of either h or r out of the first one. H is probably going to be the easiest one to substitute into. So let's rearrange the second one. Make h the subject, substitute it into the volume formula. I've now got a two-dimensional problem. Pi r squared times 12 minus r squared on 2r, which tidies up. There we go, 6 pi r minus a half pi r cubed. So if we were to draw it, we'd have a cubic. Now a cubic, I know it's got 2 turning points. One will be maximum, one will be minimum. It's the maximum one, obviously, we want. That's what we're trying to optimize. Let's differentiate. There's the VDR, there's the second derivative. Okay, we want the optimal solution. Stationary points will occur when that derivative is equal to 0. Solving that, I get 2 possibilities. So if we were looking at the graph in front of us, one of those turning points is going to be at -2, one would be +2. Now I can discount one of those solutions straight away. I mean, you're not going to make a bucket with radius -2. I guess logically, when you think about this problem, that would produce the minimum, which is one we're not interested in anyway. So I'm not even going to bother with -2. I'm going to test +2. And yes, we get a negative number, -6 pi. So that confirms what I thought. When the radius is 2, the volume will be a maximum. Now in this case, they did ask for the dimensions of the bucket. So let's work all that out. We know the radius is 2. We came up with a formula for h because we made h the subject. Coincidentally, also 2. And what was the other thing they wanted us to find? Oh, the actual volume itself turns out to be 8 pi. So we answer the question. Well, the maximum volume is going to be 8 pi units cubed, and this will happen when both the radius and the height are 2 units. So it's an unusual sort of a bucket when you think about it, because it's going to be wider than it is tall, because the radius is 2, so the diameter is going to be 4. So it's going to be a strange sort of bucket. But that would give us the maximum volume. Okay, 4h and 4i.